We've now basically finished our discussion of how to take carboxylic acids and convert them into all of the other carboxylic acid derivatives, whether that involves the direct conversion to an amide, to an ester, or whether that involves going first to something that's activated that then goes to one of those derivatives. So for example, going to an acid chloride to then go to an amide, or activating with DCC to then go to the amide. The final thing that we want to do to kind of tie this all together is to now talk about how to go from any of those derivatives and get back to the carboxylic acid. This certainly has its place, either synthetically or for other means. And so we just want to just kind of close the loop here and talk about how we can get from these derivatives back. So this subject is essentially the hydrolysis of these acid derivatives. Okay, so we can just go through these one by one. Generically speaking, this is going to be some acyl derivative, and we're just going to figure out how to get it back to the carboxylic acid. Okay, so let's start with the easy one, acid chlorides. Okay, so you'll remember that these are far and away the most reactive of the acid derivatives that we're talking about. And so if we have an acid chloride, what do we need to do to hydrolyze this? Well, it turns out to be usually very straightforward. So I would say for the majority of your standard your acid chlorides, simply just adding water is going to do the trick. So these are reactive enough that just mixing them with water, or sometimes even just moisture from the atmosphere, will cause them to hydrolyze, which can be annoying if you don't want that to happen. And so this can happen on its own. It certainly can be acid or base catalyzed. And you might just think about this for a second. If imagine that there was no additional acid that was added here, and it was just water. But the first molecule of water that adds to the acid chloride and hydrolyzes generates a molecule of HCl. And that's then a very strong acid, which can then start to catalyze the rest. So it's sort of like you only need that one domino to get this all going, at least for the acid catalyzed mechanism. So you might see if you can just draw this sort of hydrolysis mechanism. It's very much just a nucleophilic acyl substitution. Okay, so acid chlorides are very, very simple to hydrolyze. In fact, usually the problem is getting it to not hydrolyze when you don't want it to. There are some cases, incidentally, that if the acid chloride is very electron rich, or if it's very sterically hindered, that those can be a lot more stable. And sometimes you can even have them in the presence of water, and they won't hydrolyze. But generally speaking, acid chlorides are very reactive customers. Okay. The next one, sort of the next step down on the reactivity list, then would be acid anhydrides. Okay. And pretty much the same sort of consideration goes. That you don't need to think about this too hard. You basically just add water. Okay. And again, by far the bigger problem is getting hydrolysis to not happen with an acid anhydride. They're really that sensitive that, you know, if you want to keep this around, you really sort of need to keep it under anhydrous conditions for the most part, because the simple addition of water is going to take place quite rapidly to give out two different, or well, they don't have to be different, but two carboxylic acids. And again, if you think about just the simple addition of one molecule of water, that generates a carboxylic acid, which can then actually accelerate the process. Okay, so acid chlorides, acid anhydrides, these are simple. What about esters? Okay, so esters are now going to be a lot more stable generally, for the most part. And so if we just simply put an ester in water, usually nothing's going to happen, at least not on a, you know, sort of a human time scale, that we would be concerned with. And so you're going to need to do something that would catalyze this process. So you really need to be either acid or base catalyzed here. And we've actually already touched on this when we talked about the formation of esters. But remember, with the acid catalyzed mechanism, we talked about how you can take a carboxylic acid and you can treat this with acid in the presence of an alcohol, whatever that might be, ethanol, for example, and that will convert the carboxylic acid into the ester. Remember, this is a complete equilibrium process, just like we saw with acetal formation. And so in order to reverse this process, right, all we have to do is to have acid and now just push the equilibrium the other way by adding water. So that's going to push the equilibrium back that way. So the acid catalyzed formation or hydrolysis of esters is just the reverse of the formation of the ester. So, you know, again, if you want some practice at doing that kind of mechanism, by all means, take however many different esters you can think of, and you can practice those mechanisms. Okay, so the acid catalyzed works just fine. We also talked about the base catalyzed mechanism. So remember that we described this as being a process that's known as saponification. Okay, and we went through the mechanism in the ester video, so I don't know that we need to go through it again, but just to remind you, what's happening here is that you're taking an ester, whether that's a simple ester or it's a triglyceride, fat, what have you, and you're basically just going to treat this with some source of aqueous sodium hydroxide. Okay, and so then hydroxide just becomes the nucleophile, and what you're going to end up with at the end of the day then is your carboxylate. In this case is the sodium salt or whatever counterion we might have, and then you're going to spit off that alcohol. So in this case, we're talking about methanol, but whatever piece that would be, that's the alcohol you would get out. And then so you know, if this is a big greasy chain here, that's basically soap. And if you want to get that into the neutral state, then you're going to have to protonate that to work this up and get to the carboxylic acid. Okay, so ester hydrolysis, acid or base catalyzed. Neutral water usually isn't going to work unless you've got some really crazy reactive ester molecule. Okay, and so then the last major category here is amides. Okay, and so this is actually an important category because, of course, amide bonds are what proteins are comprised of. Amino acids click together via amide bonds, and so in nature, you know, your body or any living thing needs to be able to not only form amide bonds, but also to destroy them, to cleave these amide bonds, you know, they need to destroy proteins when they've passed their due date, or you know, enzymes that are going to digest food. You eat a big steak or a big tofu dinner, you have a lot of protein. Your body actually has to use enzymes to break apart these amide bonds, and so that's basically a hydrolysis of amides. We're more concerned with a sort of laboratory type of amide hydrolysis. Okay, and in the laboratory, really the cleavage of amides is not so easy to do. Okay, they are not so easy to hydrolyze, and I would say for the most part, this isn't a procedure that chemists do a lot, at least not on the sort of academic laboratory scale. If you have an amide, that's usually going to be your target product. That's the thing that you want to get, and using an amide to get or you know, to go through an amide intermediate to get to a carboxylic acid or to get to an ester or whatever, is usually going to be a bad strategy, just because this hydrolysis business can be so hard. It can be done though, as you might imagine, that just the neutral water is usually not going to do the job, at least on any reasonable time scale. And so if I have an amide and I want to hydrolyze it, I'm going to have to use acid or base catalysis. So acid catalysis can work. So if I treat an amide with HCl and water, this can catalyze the hydrolysis, but you're really going to have to add some heat here, usually. So boiling water in HCl, for example, even then, I still would expect this to be a pretty slow process. But what this will do is it can hydrolyze these amides. And then, right, so I say here that you would spit off the amine piece, right? That piece there would get spit off. But of course, if we're under HCl, that is going to become protonated. And so we would get to the ammonium salt here. So that, and that actually serves as a driving force. So once you get to the ammonium, it's no longer viable to go back the other way. At least on a reasonable scale. Certainly if we're in water, we're pushing the equilibrium all the way to the right. Okay, so this can happen. What would the mechanism be? You probably could figure it out on your own at this point, but essentially what we're going to do, as we've always done, if we have a carbonyl and we've got some proton around, we're first going to protonate that carbonyl, okay, and that will give us this protonated species. It's now activated to undergo nucleophilic addition of the water. And now, as we talked about, right, this is not so electrophilic because the amide nitrogen is really dumping in electron density here. So it does get activated by being protonated, but it's still not so electrophilic, and water isn't a very good nucleophile. So this is the problem step, right? The problem is getting the water in there in the first place. Once you do that, though, you get to your tetrahedral intermediate. Okay, there's our water we just added, and of course we need to deprotonate that. Okay, so we will get to this intermediate, right? And of course we could protonate one of the hydroxyls, and that's actually just going to lead us back this pathway. So instead what we need to do is we need to protonate this nitrogen so that we can turn it into a reasonable leaving group. Okay, so if we do that, okay, we've turned that into an ammonium, and now we're just going to use the lone pairs of the oxygen, eject that ammonium group. Okay, so we just were able to spit that off as a neutral amine, and then as I set up here, that's going to react with HCl to form ammonium chloride. And here we have an oxocarbenium, and we just simply need to finish this off by deprotonation. Okay. Okay, so really it's exactly the same as we've seen before. It's the same as the ester acid catalyzed hydrolysis. It's just in this case we're dealing with a nitrogen substituent, and that just kind of just makes things harder, makes things harder to hydrolyze. But mechanistically speaking, it's really kind of the same type of thing. So we can do acid catalysis. Now, in theory, we could also do base hydrolysis to cleave amides. But this is actually just very hard, and really this isn't a synthetically useful process for the most part. So if we have an amide, right, so what we're asking this to do is to have hydroxide add as a nucleophile. Okay, that's fine, but then we would get to this kind of intermediate, and at this point what we need to have happen if we're strictly dealing with a base mechanism is now we'd be asking an O- to spit out an N-. Okay, and that just actually turns out to be a little bit too much to swallow. Okay, so that's the hard part really, and so that's what makes this really just not very plausible. Now, of course, as we've talked about, this proton accounting that it's a little bit of fiction, and in reality, you would be able to shift protons around if you're in water, even if you're under hydroxide. So if you put an amide into sodium hydroxide solution and then heat it up, I'm sure that you could get this to happen to some extent, but it's still not going to be a very fast process. And for anything that has even a little bit of complexity, it's not going to be a useful thing. So for the most part, we're not going to like to deal with base catalyzed amide hydrolyses. Okay. All right. So that's essentially it. We can kind of now we know how to go from carboxylic acids to the derivatives, and now we know how to go from the derivatives back to carboxylic acids. So what I want to do, just to kind of finish this off, is to give you a little bit of a chart that shows all of the different interconversions that we're capable of doing now. So I'm going to put carboxylic acids at the center because that's sort of the place where we can access any of the derivatives, and we've now also talked about how we can convert some of these derivatives to one another, and how we can convert the derivatives back to carboxylic acid. So let's just put all this together and see what this looks like. Okay, so we talked about that we can absolutely go from an acid to an acid chloride, and we just covered how we can go from an acid chloride to an acid. So that's absolutely possible. We talked, of course, about how we can go from the acid chloride to any of the other derivatives. Okay, so we can go to anhydride, we can go to ester, and of course we can also go to the amide, right? So all of those are a piece of cake. Of course, to the acid anhydride, we talked about how we can certainly go to the amide. We can definitely go to the carboxylic acid, and we can definitely also go to an ester. That would also be a viable interconversion, okay? All right, so we can go from carboxylic acid to anhydride. So we could do this with a DCC coupling, for example, or more usually we would go through the acid chloride. We can certainly go from acid to ester and back again, right? So acid catalyzed can go both ways. Base is going to go only that way, but we can certainly interconvert. We can go directly from an acid to an amide, and we can go back again. As we just talked about, going back again isn't so simple, but we can certainly do it. It is technically feasible. And one thing that we didn't actually cover, but is also certainly possible, is you can go from an ester to an amide. Okay, so what you would do is you would essentially treat an ester, for example, with an amide. So the anion of an amine would certainly work, and you could probably get away with doing some acid catalyzed type of process as well. It's a bit unusual to think about doing that, but it would work. It would absolutely work, and certainly in an intramolecular setting, that's actually going to be very favorable. Maybe there'll be some problems on the problem set that deal with that type of aspect. Okay, so those are all the things that are possible, but there are some things that are not possible here, and so I'm gonna do these in the magenta. So as we said, there's sort of a way that we can go from the most reactive to the least reactive, but going from least reactive to most reactive directly doesn't work. So what we can't do is we can't take an amide and go to an anhydride. We can't take an amide and go to an acid chloride, and we can't take an amide and go to an ester, at least not under very nice conditions. Okay, We also can't take an ester and go to an acid chloride. We can't take an acid anhydride and go to an acid chloride either. Okay, so all of those are basically not possible. All right, but anything with the yellow arrow is possible. Okay. Oh, and yep, one more. We can't go from an ester back to an acid anhydride. Okay, so all of those are going uphill. We can't do it. The only way that we can do it is to go from one of these, go back to the carboxylic acid, and then we can either go directly to one of the derivatives or go to the acid chloride and then come back down the hill again. Okay, so that's sort of our whole reactivity rubric to keep in mind. Okay, so that's sort of the nuts and bolts of how to interconvert carboxylic acid derivatives.